at your seminar. So I'm going to talk about a project which I did with my student Ryan Russell when I was at UCI. It's about one simple question. If you have some questions or comments during the talk, please feel free to ask. I will try to cover. I don't want to cover all slides, but at least I want to tell you what's the problem, what's the motivation, and how did we solve that problem if there will be some time left. So what's the question? Take any Gaussian vector, standard Gaussian vector with mean 0 and covariance matrix identity. And take any smooth function from Rn to R. And the question we want to understand is the following. Under what conditions on the gradient, how it should decay, or what information we need to know about the gradient so that we can make sure that the average of e to the f of x is finite. Okay. Here are some remarks. If the gradient is bounded by 1, if absolute value is bounded by 1 at every point, in other words, the function is 1 Lipschitz, then this is true because, I don't know, you can see it's 1 Lipschitz, it's bounded by a linear function, it doesn't grow linearly, so you have here e to the absolute value of x, and when you integrate with Gaussian measure, the square decay, e to the minus x squared, it will be finite. So this is kind of simple case exercise. Now let's require a little bit less. This is pretty strong assumption. Let's say that in average, the gradient f of x is finite. Does it imply that the exponential integral is finite? The answer is no. It does not imply. It's too weak requirement, because here is example. Let's take f of x equals the norm of x squared. Then you can see that the gradient is finite because gradient is of order x. When you integrate with Gaussian measure, it's finite. But this guy will be infinity because, well, right, you have e to the x squared, and then you would integrate e to the negative x squared over 2 dx. So this will be infinity. Okay, let's see what, so this is not enough. Let's require a little bit strong assumption on the gradient. Let's say that average of e to the gradient of f of x is finite. Will it imply that the exponential integral is finite? The answer is no in this case as well. And example is the same example. Indeed, right? Because let's see. The gradient of f for this function, it's approximately c times, I think, 2 times or square root of 2 times the norm of x. And clearly in this case, this integral is finite. But this one is infinity, as I said, because it's the same example. So it's not enough. So we need to require something much stronger on the gradient to conclude that this exponential integral is finite. Okay, here is the theorem of Babkov-Götze. They proved it says the following: if you take a function and you assume that it has mean 0, let's say x is the standard Gaussian vector, then average of e to the f of x is bounded like this. Average e to the a times gradient f squared, and everything to the power 1 over 2 to 2a minus 1. And this is true for any real number a, little a, greater than 1/2. Now, okay, before I say their motivation is, they were studying what is called measure concentration phenomena. For example, this one way to prove measure concentration for the standard Gaussian random vectors is, you prove log-Sobolev inequality, and then for one Lipschitz functions using Herbst argument. Perhaps some of you have seen. If you have not seen, this is fine. By Herbst argument, you can conclude measure concentration for the Gaussian, for the one Lipschitz functions. But they are concentrated around their average, and the tails decay like e to the negative t square over 2. But what was the goal of Babkov-Götze was to kind of characterize random vectors for which, for one Lipschitz functions, we have measure concentration phenomena. And what they did is that, for example, let's talk about standard Gaussian. Standard Gaussian random vector, they proved this estimate. Now, how does one conclude measure concentration from here? If you apply it to lambda times f instead of f, and you assume that f is one Lipschitz. Oh, let's say the grade f is bounded by 1. Then this estimate implies that e to the lambda f average is less or equal. Now let's estimate gradient by 1. So we get, here we will get average e to the a times lambda square and everything to the power 1 over 2a minus 1. So assume that the function is 1 Lipschitz. And from here, so this is constant. And then now if we take a goes to plus infinity, what do we get? We get that this equals e to the lambda square over 2. And this estimate now, so we got for one Lipschitz function, we got that this guy decays like e to the lambda square over 2. And there is the standard trick, use Markov's inequality to conclude measure concentration for one Lipschitz function. So I want to say that kind of the main ingredient in the proof of measure concentration is this estimate. And it just directly follows from this beautiful inequality that Babkov-Götze proved. And what they proved was slightly general. In fact, they show that this estimate holds for all random vectors which satisfy what is called log-Sobolev inequality with constant 1. I'm not going to write what it is, but I want to tell you that the Gaussian vectors satisfy log-Sobolev inequality with constant 1. So in general, they proved it for a large class of random variables, and they got measure concentration for a large class of random vectors. Okay. Now, if we look closely at this estimate, in particular, we can see that this expression is finite if e to the average of e to the a times gradient of f square is finite for some a greater than 1/2. So in particular, it kind of answers the previous question. But what happens with this estimate is that if you take a equals 1/2, if you just take, then this blows up, it becomes infinity, and this inequality fails down. So you are kind of getting 1/2, but this power becomes infinity, and this inequality fails. At that critical exponent, when a equals 1/2, Babkov and Götze, they asked the question, is it true that if, so here is their question, is it true that if this integral is finite, it implies that this exponential integral is finite? Okay. Any questions about this question? They are assuming that the average of f is 0. This is a very mild assumption on the function. If you know that this is finite, you can kind of, by Jensen's inequality, you can conclude that e to the f should exist. But if you want to find condition in terms of gradient, then e to the negative f should exist. So in particular, e to the absolute value of f should be finite average. So you can say that function is integrable at least. Well, anyway, this is a very mild assumption. It will be always assumed throughout my talk. And the question is, does this imply this? Okay. And in their inequality that they proved in the previous slide that I showed you, it's a very sharp inequality. Actually, you cannot replace, for example, in this, you cannot replace here this a, this power by something smaller. Let's say a divided by a multiplied by 0.9. You cannot replace by a small number. You cannot also replace this power by a small number. So it's a very sharp inequality, but surprisingly, it just breaks down at that critical exponent. And it doesn't give you the answer. Maybe it's infinity. Maybe the answer to this question is negative. Okay, that's their question. And Talagrand showed that the answer is yes. Talagrand's proof was not published. But if you read Babkov-Götze's paper, they say in private communication, Talagrand showed that this is finite. So I don't know exactly they proved in dimension 1 or Talagrand. No, Babkov-Götze, they asked even this question in dimension n equals 1. No, I assumed, you know, if you prove in n equals 1, perhaps you would also prove in higher dimensions. So I assume that Talagrand's solution was in all dimensions. And the main theorem that I want to tell you is the following. So here is what we got. If average of f is 0, then we have this estimate for the standard Gaussian random vector. E to the average of e to the f of x is bounded by e to this exponent 10 times average e to the gradient square over 2. And this exponent is multiplied by this number. This exponential function is multiplied, but not by this factor, which is which I want to talk a little bit right now. But first, let me say that this estimate holds in any dimension. There is no n involved. That's one thing. Another thing is that, you know, unlike saying that if this is finite, it gives you quantitative bounds, right? It tells you that this expression, you know, if this is finite, then the right-hand side is finite because this is less than 1. And this is finite. So you get e to the 10 times finite number. So it bounds, it tells you that this exponential integral is finite. So in particular, it also answers this question, but another observation is that it sharpens this kind of this question in the sense that it also puts this extra factor, which is 1 plus gradient of f, everything to the power -1. It could be that this expression is finite and this is infinity, but this is still finite. So we also have this extra factor, which which kind of sharpens this result. And I want to say that this factor that we got, 1 plus gradient of f to the -1, you cannot replace it, this -1, you cannot replace by a constant c, which is greater than 1. You cannot replace by a higher power. So 1 is kind of sharp. You cannot do better than 1 here. And the example is this example. So let me just show you that this example shows you that this estimate, kind of this factor, this power is sharp. Let's take f of x1 comma xn equals x1 square over 2. Now, what is left-hand side? Yes, I understand that we want average to be 0. Okay, perhaps subtracted some average, but okay, let's don't subtract because we know that average of this function is finite. So left-hand side is 1, right? Now what's the right-hand side? the right-hand side, we have e to the 10 times e. Now, if I calculate the gradient, I get, for this, I get derivative. So which is just x1. Then I square it and divide by 2, because here is division by 2. So I get e to the x1 square over 2 times 1 plus, and the gradient is like absolute value of x1. And this is to the power -1. X1 is first coordinate of the standard Gaussian random vector. So when you integrate, if you calculate what is this average, this cancels with the standard Gaussian density. The function depends only x1, so the density of the Gaussian will be e to the -x1 squared over 2 divided by square root of 2 pi. And what remains is this integral, and we know that this integral diverges. I'm sorry, this what I want to say. Yes, if you put here power c, where c is greater than 1, then this integral converges, and this is finite.
So the left-hand side is infinity, right?
Yes, left-hand side is infinity.
And that's what you wanted to show, right?
But left-hand side is 1. I think I want to take...
yeah, left side
yes.
is infinity, yes.
Right. I'm sorry. Left-hand side is infinite. Why did I apologize. Left-hand side is infinity, and if you put constant c, which is greater than 1, then this is fine. This number is finite. So you cannot put here. You cannot have. You cannot have this expression is finite with some c greater than 1. But when c equals 1, we see that this also diverges. So this is possible. Okay. Okay. And one thing, as I said, is this estimate is dimension independent. It does not. There is no n involved in this, and it's kind of sharp in the sense that this factor is sharp with this factor is sharp with -1. Okay. Now,
by the way, excuse me. By the way, the condition expectation equal to 0 is irrelevant, yes, because the right side does not depend on the constant.
Right.
Just the left side, you subtract the constant, yes.
Exactly. You can just subtract here average of f and forget about this.
Right. Yeah. Thank you.
We can write in this way. Okay. Now I want to say I want to talk about some related results that people have studied. Yes, before I say some related result, let me make one remark that it just follows from this theorem. There is a Caffarelli's contraction principle that the theorem also holds if you would replace Gaussian random vector by some random vector which has this density e to the negative function u of x dx. And the only thing you know that the Hessian of u is greater or equal identity matrix. So if you replace Gaussian by any random vector which has log concave density, so that Hessian of this power is greater or equal to identity, then this is still true. It just follows from this inequality using some kind of using certain arguments. So if you manage to prove something for the Gaussian, you manage to prove it for uniform log concave vectors. That's the main message. Okay. Now let me say briefly about the related results that people have looked. One thing is that I found in the literature is, you know, if you take, so everywhere we will have average equals 0, but as you said, you can look at f minus average of f and rewrite all the estimates with minus average. Now, people have studied exponential integrability for random vectors which have certain distributions. And here is what is known. For example, if y is uniformly distributed on the sphere of dimension 2, on S2. Then this estimate is known that exponential of e to the f of y is bounded by e to the average of, here is a spherical gradient, square divided by 4. And as far as I remember, as far as I know, this is Moset-Rutzinger Onofre inequality, and Onofre kind of found its best constant here. The question was if one can, I think it was with large constant known, but Onofre found here that you can put 4 and you cannot put anything larger than 4. 4 is the best constant. And it has some applications in differential geometry. So this is something they proved it using variational calculus, writing Euler-Lagrange for optimizers, studying the solutions of this PDE, and saying that optimizers should have this form. That's how they prove this estimate. And it's a quite popular topic. I don't know, Moset-Rutzinger estimates. Another thing I want to say is the result of Carlson-Chang, which says that if y is uniformly distributed on the unit disk, then there is this estimate. It's written in a little bit strange way, e to the power 1 plus average of this. You know, after this results, then people wrote some other papers which say that actually this implies this by doing some change of variables, but this was noticed later. But anyway, this is, I think, the first time it was due to Carlson-Chang. And the last, so here is the usual gradient. Now it's a smooth gradient on the unit disk. And the last thing is if y is uniformly distributed on the vertices of the, what I call Hamming cube, these are vectors of length n with coordinates plus minus 1, then there is this estimate due to Babkov-Götze where this d, I'm not writing down what it is, it's a certain discrete gradient which is defined in a certain way. Maybe I will get there. Maybe I will use this discrete gradient in my talk. But anyway, it's a pretty close to, you know, if it somehow measures derivatives of the function. And this is what was known. And this kind of question that I'm asking, I'm not saying that it's a very, very important question. It's just a question of this type that you know some information about the gradient, some integrability, and you want to conclude something about function or about exponential of this function. For example, one very, very classical result is Gagliardo-Nirenberg inequality, which says that if you take compactly supported smooth function and you know that the gradient of f is L1 is integrable in L1 with Lebesgue measure on n-dimensional Euclidean space, then this always dominates. So you can conclude that f is in Ln over n minus 1 in this space. And this is kind of very classical result, and it's kind of also has this property that you know some information about the gradient and you want to conclude something about the function. Okay. Now I want to say that the proof of the theorem that I wrote is very short. I can fit it into one slide, and I will show you. And you will see the proof, but it's this kind of proof that you know what they call zero knowledge proof. You see the proof, but eventually you don't learn anything. You kind of get the zero knowledge. So let me show you this proof, and then I will talk about how could one come up with this proof. So here is the proof. It will be in one slide. Let's take heat flow. Let's take a function. And let's take heat flow in a probabilistic way. You can write as g of x plus Brownian motion at time t, and then you averagize over the Brownian motion. And let's consider time when t goes from 0 to 1. I don't want to go to look at the times when t is greater. It's another kind of fancy way of writing the heat flow. You can write as convolutional with the Gaussian kernel, but I want to write in this way. Now let's consider the following function, which is, so what is written here? X1 is the first coordinate of the standard Gaussian. So it's a standard Gaussian one-dimensional random variable. Let's look at the probability distribution function. When probability that x1 is less or equal to r, let's take the logarithm and let's take the derivative, logarithmic derivative, and then let's again take negative logarithm of this result. Okay, it's like negative log derivative of log of the distribution function. So this function is defined for any r, for any real number r. And let's consider this complicated function. You know, I'm not saying where does it, I will talk about this. As I said, it's a zero knowledge proof. So let's consider this function, which is integral from 0 to y e to the, and here's what happens. You take derivative of k of this, and you take the inverse, you consider at point t, and then you compose. So it's k of argument k prime inverse of t dt. Well, one needs to explain why this k prime inverse exists, why derivative is invertible of this function. But let's, these are some technical details, and the answer is yes, it is. And this function is defined for any y greater or equal to 0. Then the claim is that for any function g from Rn to 0 infinity, positive function, let's say smooth, if you want bounded, so that this heat flow, everything exists, is unique. For any function, the following holds. If you look at this aggregate, I take this f, and inside I plug this ratio. It's a heat flow at time 1 minus s of g. Here is square root of s, and here is absolute value gradient of p1 minus sg. This is of f, then log of p1 minus sg. So you look at the result, it's a function of x and s. And then you take again heat flow in variable x, and then you get a new function, and then you plug x equals 0 in the result. The claim is that this function increases on 0, 1. Well, you know, the rest of my talk, I'm going to devote explaining why this quantity, why the heat flow, where this function f comes from. But let me, as I promised, let me finish this slide. Now, if we apply this claim to function g equals e to the f, it's a positive function. Then at time s equals 0, let's see, we are going to get logarithm average of e to the f. You know, this is this exponential integral that we are aiming for. But here is with logarithm. It's okay, you know, think that I'm trying to prove the inequality, but I took logarithms of the both sides in the theorem that I showed you in the 2 slides before. This equals a0. Let's see, why is it a0? If I plug s equals 0, this is 0. So this is 0, everything is 0. F at 0 is 0 because f of 0 is 0. It just follows from this integral. So what do we get? S0, you know, if you take PS, heat flow, right? P at 0 of G equals G. At time equals, T equals 0, we get the function G. So what we get is that logarithm P1 of G at point 0. Now, when T equals 1 and you plug X equals 0, you get Gaussian integral of function G. So indeed, what we are getting is that average of G of X, which is a logarithm average, which is exactly this. So left-hand side, hey, this is true. This I just showed you that this is true. Now, when you plug S equals 1, I said it increases, right? So when I plug S equals 1, so let's plug S equals 1. What do we get? We get P1 logarithm of G plus, now what is here? F of, I think, gradient of G divided by G. And P1 at 0 is just Gaussian integral, right? As I said. So what you get is that you get average of logarithm of G plus average of f of gradient G divided by G. Now, if I take G equals e to the f, I get exactly average of f, which is here. And you know, if you differentiate the exponential function, you get e to the f times gradient of f. So you just get this expression. Okay. And that's it, because then is one technical claim which says that this function that I wrote, it is bounded pointwise by this expression that I had. So eventually what we are going to get that this is less or equal average of f plus average 10 times e to the gradient f square over 2, 1 plus gradient f to the power minus 1. You know, if you take exponential of both sides, you get exactly the theorem that I wrote. So assume that average of f is 0. So that's kind of the proof of the theorem. As I said, it's a zero knowledge proof at this moment because there are 3 questions. One question is, why do you consider this quantity? Where does it come from? Or how did we construct this function, right? How did it appear? Another question, which I think is the most important, why heat flow? So why there exists some monotone quantity which kind of interpolates the left-hand side and the right-hand side, and why does such function exist? So my goal up to the end of the talk is to explain, you know, at least to give you an idea how we construct, why we construct heat flows when proving such type of estimates. I don't know. Perhaps you have seen Bakri, Gentil, Ledos diffusion semigroup, very beautiful book. And what they do, they prove Poincare inequality using semigroups, Ornstein-Uhlenbeck semigroup, or heat flow arguments. It's a very beautiful book, and you know what I'm showing you. It's of this type. It's a proof of this type, but it's a different, of course, because now we have different function here and some different expression. But you know, in that book, there is one thing I was always I found it always kind of intriguing, that why would one consider semigroup? Why one starts with heat flow? Where does this come from? Why? How does the heat flow appear? And so I will try to explain this. In this proof, there are certain building blocks, and I will try to explain one building block which should tell you how does the heat flow arises and what was kind of the tool we've been using when proving this this estimate. So let me start from so you know, if you have not listened what I talked, you can forget, and let's start from the new page. What is Jensen's inequality? It says that average of B composed with G is bounded by B average of G for all test functions, if and only if when capital B is concave function. It's a Jensen's inequality. Now, I want to ask the same type of question, but now there will be gradient involved. So I give you an arbitrary function m of 2 variables, x and y, and I want to ask when average of g of x gradient g of x is bounded if I would take this average and put in front of g, like here. I want to write this Jensen's inequality, and I'm asking you on what should be the conditions on m, on capital M, so that this is true for all smooth functions g. Well, but now notice that if I put average in front of g and g, then this is constant and the gradient will be 0. So in particular, we're getting a little bit strange right-hand side, but it's okay. You know, I'm still asking a question in the framework of Jensen's inequality. And for the Gaussian random vector, it turns out to be there is a very nice answer. And this is not very well known inequality. You know, I have not seen in the literature written like this. It says the following. Well, it's not if and only if. Here we have if and only if. It says the following: if this matrix, what is it? Here we have partial derivatives m of x plus my over y, I want to assume that y is greater or equal. Okay, let's say y is greater than 0. You know, when you put gradient, this argument is always non-negative. This matrix is negative semi-definite. You know, without this, it would be just concavity, right? Without this term, it's just exactly the Hessian is negative semi-definite. We are in the classical Jensen inequality. But here, due to the gradient, due to this structure of the gradient, we're adding one extra term in the first coordinate of this Hessian. So if this matrix is negative semi-definite, then this Jensen inequality holds true. And unfortunately, this is not if and only if. It says that if, so it's pretty strong assumption. It could be that M is not like this. M is not like this, but this still holds true. Unfortunately, we don't have if and only if answer. And that difference makes Gaussian world very interesting. You know, the estimates with gradients, sometimes people use different techniques to prove estimates which involve gradients. So by using only this theorem, you cannot prove all estimates. That's what I want to say, which involve gradients. But you can prove pretty much most of the estimates that we have seen: Gaussian isoperimetric inequality, Bobkov-Götze, log-Sobolev inequality, Poincare inequality. All these estimates you can prove by constructing a certain function M. Now, I want to say that this was kind of one important building block when we were proving the theorem. Our goal was to kind of construct certain function M. You know, now we have estimate which involves G and the gradient G, and then the goal is to kind of match the left-hand side and the right-hand side so that this, you know, okay, if you take negative M, inequalities will be reversed. So, you know, we will be able to bound the gradients from below in terms of the averages. So I plug G equals e to the F. Okay, I'm not going into details, but I'm saying that this was kind of the main building block, and using this theorem, okay, I'm not saying it's trivial, but it also requires some work to eventually solve that problem. But this was kind of a main tool. Therefore, let me just tell you how do you prove this theorem, okay? And here is how to prove such theorem. Assume that X is one-dimensional. Let's consider a simple case. One-dimensional random vector function is on the real. Here is my Gaussian vector. The Gaussian vector we can approximate by, you know, you take independent Bernoulli plus minus one random variable symmetric with probability 1/2. You take the sum, square root, they, by central limit theorem in distribution, they converge to X. Okay. Now let's ask a simple question. You know, can we, instead of proving with Gaussian random vector, can we just try to prove with, instead of Gaussian, I plug this? Can I prove this estimate, this kind of discrete inequality, and then I just take n goes to infinity? And maybe if once I take n goes to infinity, I will recover this estimate. So what should be the right assumptions on M so that this inequality holds for all G and for all N? Okay. Okay, how can we answer this question? Now, in this question, I like everything except I'm not happy with the derivative. You know, if I just had, instead of derivative, I had G, but you cannot have, but suppose, you know, if I had, it would be eventually inequality about some points, some finite number of points, maybe one could approve. So let's do the following. Let's take this derivative and replace it by a discrete derivative. What I wrote here is that it's an exercise that you can see that G prime at this sum, you can replace by square root of sum from J from 1 to N, the square of the following. You take G at the sum, divide by square root of N, and then you subtract on Jth position, you put negative sign. Divide by square root, divide by 2, square it. And I'm saying that for large N, this is almost equality. It's actually, if you want, it's equality up to this error term, capital O of 1 over square root of N. So when N goes to infinity, you are getting equal. So when you take the averages of both sides, you can kind of replace derivative by discrete derivative, kind of these finite differences. Now, one advantage is that prime disappears. You know, I have my function G, and this will help us very much. Now, this expression may look a little bit complicated, but it's not something we invented, this discrete derivative. It was known in analysis of Boolean functions. This is what people call influences, especially when they put averages inside. That's essentially how this expression appears. So let's take this, let's replace G prime by this, and let's call this right-hand side by this letter. So what we want to prove, we want to prove this estimate. So I'm replacing derivative by this, but I know that when n goes to infinity, this behaves like derivative, and eventually by central limit theorem, we are converging to the Gaussian measure. So at this moment, we posed a question which does not involve derivatives. It just involves function and epsilons, okay? Now, what's the advantage of this? Here is one way to prove such estimate. You have epsilon 1, epsilon n. Let's ask a simple question. If I just take average with respect to epsilon j, let's take some epsilon j. So when epsilon j equals 1 plus the same thing when epsilon j equals -1, divided. Let's freeze all other variables. Let's just ask a simple question. Take this average and put inside here. That's what I wrote. Let's ask a simple question. Under what conditions on capital M we can do this? Suppose we can't do this, then what we will do, we just take the big average, which is this one, and we will just split it epsilon 1, average epsilon 2, etc., average epsilon n. And then we will be iterating, we will be putting averages one by one. We will be applying this inequality star n times, and then we will be putting all averages. Eventually, we will put all averages here, we will get 0 eventually. So we will get the right answer. That's what we're going to get eventually. So we're asking a simple question. I freeze all variables except of epsilon j, and I'm asking when I can put average on epsilon j inside n. So this kind of Jensen inequality. So that's the question that I asked. And if you think a little bit, this one is actually a question about numbers, right? You can think that when epsilon j equals 1, it's some number, let's say capital A. When epsilon j is -1, it's some number, I'm sorry, this is A and this is B. So this expression, so what I'm saying is this guy takes two values, capital A and capital B. When epsilon j is 1, epsilon j is -1. And here also G is involved. And you can also express everything in terms of this of numbers. What I'm saying that, after a little bit of work, you can show that this is the same, what is written here, it's the same as asking this inequality. That function m satisfies this strange inequality where in the first argument you have concavity, in the second argument you have something strange. You want to ask this inequality for all numbers x, a, y, and b, this kind of 4-point inequality. If we did not have this, it would be just concavity. In the first, if we didn't have the second argument, it would be just concavity. Well, and that would be kind of end of the proof. We would prove it if we could verify this inequality. We would take this limit in the central limit theorem, and that's how you would prove one-dimensional case. But n-dimensional case is also kind of also the same thing. There is sometimes a product argument, but it's also the same thing. But here is a difficulty. Difficulty is that to verify this inequality, which seems pretty easy, it's not easy. It's really complicated, especially when your function looks like this. I can tell you a priori what function we'll be taking. We'll be taking this function. It will be this function. Okay, I'm not explaining where does this function. It's another story. We are looking for the solutions of this. I wrote some matrix. Matrix is negative semi-definite. We are looking for solutions, and in that class we found this function. But what I want to tell you is that to verify this estimate for 4 numbers for this function, which is kind of defined here implicitly, right? It's really complicated. We don't know how to verify. I think this is true, but I have no idea how to show. On the computer, I checked it and it works, but we don't know how to prove it. If you would prove it, you would prove this theorem on the discrete, even on the Hamming cube. not just Gaussian space with Gaussian random variables. At this moment, is there a way to cheat a little bit? And there is a way to cheat. And here is, let's make one observation. You know, the way, how to cheat, what do I mean? You know, the thing is that we actually want to prove this inequality when n goes to infinity. You know, at infinity, we don't really want to prove for any n, for large n. So maybe there is some chance. We don't really want to verify this big, complicated 4-point inequality. And here is one observation. If you take little a, this little a goes to 0, and you tailorize left-hand side, you write the first order terms, they will cancel with this constant, and first order terms will cancel each other, and second order terms will remain with a square. And then you will see that second order, the necessary condition is the second order term should have the right sign. And what it means is that if you rewrite, it means exactly that this matrix is negative semi-definite. That's where this condition appears. You see, we are kind of seeing that this is maybe under this assumption, only under this assumption, we can get the inequality with Gaussian random variables instead of this. You know, this implies this, but not the vice versa. I won't say that this infinitesimal does not imply. There are examples when this implication fails, unfortunately. Okay, maybe, you know, there is a crazy hope that maybe just using this, we can still prove the inequality. And we know the answer is yes, because I showed you the theorem, but let me show you in 3 minutes, in the remaining 2 minutes, how does it work? As I said, we want to put epsilon j's one by one. This will be denoting average with respect to the first k variables. And this will be denoting average, okay, it doesn't want to write this. This will be denoting average with respect to the remaining variables, k plus 1 up to epsilon n. You know, if you take, why I cannot write? Okay, my pencil stopped working. Perhaps battery, there is some issue. But anyway, I will be just talking on the slide. You know, when you put one epsilon j, when you iterate once, you can iterate k times. You know, you put average, you put once, twice average inside, then you put average, let's say m minus k times inside. What you really want to show is that this mapping is decreasing in k. You averagize with respect to the remaining k variables, and then you put inside averages with respect to m minus k variables. That's what you want to show, that this function decreases as a discrete function k from 0 to n. It's the same thing, you know, it's not quite, but it's a weaker statement. Now, proving this, here is one remark. If you look at the first argument, average over variables n minus k, the remaining n minus k variables, you can write like this. And so here, and the second argument, you can write also up using some Taylor's formula, you can write like this. It's average with respect to n minus k variables. So after simplification. And the claim is that if you take k and n goes to infinity so that k over n converges to s, fixed constant, which is from 0 to 1. This fact that this discrete map is monotone, you know, after taking the limit, you can see that it implies that this map is monotone, that map S. So I'm missing G here. You know, B is Brownian motion at time S. B tilde is the independent Brownian motion of B. So it implies that if I would averagize with respect to B tilde, then M of average with respect to B of G, there is letter G is missing, of B tilde S plus B1 minus S. Well, it converges to this, and this is exactly, you know, if we would have known that this discrete map is decreasing, then it would imply this continuous map is decreasing. And okay, that's the last slide. And this continuous map is decreasing. It's the same thing what I wrote here. It's this, you can write in terms of heat flows. And you can just ignore all this discrete computation. You can just try to take derivative in S and prove that this continuous map is decreasing. That's how heat flow arises. And then if you integrate by parts, I don't know, 4 times, you will see that necessary condition is that this matrix is negative semi-definite. And that's how you would prove it. But at least I wanted to show you how this heat flow arises using this Bernoulli symmetric plus minus 1. You know, it's very natural approximation of the Gaussian random vector using central limit theorem using this epsilon i's, and then you just prove by on dimension, you prove 1 by 1, and then you take the limit, and that's how you recover the heat flow. Okay, thank you very much. I apologize that my pencil stopped working. I couldn't point out to the right arguments. Okay.
All right, thanks very much.